Hello students, in this video we'll see how to construct the matrix that corresponds to rotation anti-clockwise about an angle theta. Let's consider the linear transformation. Corresponding to rotation anti-clockwise by theta radians. Okay, and so what's the idea? Why don't this is a linear transformation? Because if we think of if we have a vector over here, A, there's a vector A, and then there's a vector B. Okay, and so of course what I do to find A plus B, so I draw this diagonal over here, and so that vector over there is going to be A plus B. That's the vector A plus B. Now if I rotate A by theta and I rotate B by theta, so if I rotate these vectors over here, so if they rotate by the same, that goes to A, and that goes to B. Well, then with the same principle, I have the same parallelogram over here. And then my A plus B's over here. So that's the rotation. That's R theta of A. That's R theta of A. That's R theta of B. And that, of course, is going to be R theta of A plus B. In other words, the whole parallelogram is rotated by this angle theta, so I know that it preserves the linearity. And simply by scaling, if I scale A by lambda, right, if I do R theta of lambda times A, right, well, that's the same as just doing R of A and then scaling by lambda, right? In other words, R is indeed a linear transformation, okay? So I would like to figure out what the matrix representation for that linear transformation, okay? So question, what is the matrix representation of this linear transformation? Okay. So let's draw a configuration. So here's the configuration which will help us. Here's the x-axis, here's the y-axis. Here's a vector over here, xy. And this vector is going to come, that has a bearing of angle alpha with respect to the positive x-axis, okay? And then what I'd like to do is I'd like to take this vector over here and just rotate it by theta radians. So that angle over there is a rotation of this thing by theta. Now the key feature when we rotate is that the lengths do not change over here. It's an isometry. It doesn't affect the lengths over here. So this length over here is going to be L, and this length over here is also going to be L, okay? And so now what I'd like to do is I'm going to call this point over here x prime, y prime, x prime, y prime. I like to find a formula for x prime, y prime in terms of x and y and theta. Okay, so let's do that. So of course, I know what x, y is because I can draw a triangle down over here. So draw a triangle. A right triangle like that. And so of course that's my x and that's my y. So I have a representation for x and y. My x is going to be what? It's going to be L cosine of alpha, because the cosine is the adjacent over the hypotenuse. My y is L sine of alpha. And then my x prime, y prime, I can also draw a triangle for them. Okay, so what will x prime, y prime represent? X prime, y prime. X prime is equal to L cosine of alpha plus theta, and y prime is L sine alpha plus theta. And now I can use angle addition over here. So my x prime is going to be what? My x prime is going to be L times the quantity cosine alpha, cosine theta, and then minus the sine of alpha, the sine of theta. That's my formula for my x prime. And my y prime is going to be L. And then the angle addition formula for sine is the sine of alpha, the cosine of theta, plus the cosine of alpha, the sine of theta. Great. Now let's examine what these things are. we can simplify this quite a lot because we can simplify this in the following way. We can notice over here that L times cosine alpha is going to be what? L times cosine alpha is going to be my x. L times sine alpha is going to be my y. And similarly, L times sine alpha is my y. And then L times cosine alpha is my x. So what does this simplify to? This simplifies to x times the cosine of theta, and then minus y times the sine of theta, minus y sine of theta. And my y prime simplifies to what? Simplifies to, what's the x going to be? It's going to be a cosine of theta. Let's see, the sine of theta, rather. The sine of theta is my x. So I have a sine of theta x sine theta. And then plus y cosine theta, plus y cosine theta. And so now we're in a position, so now I see what my transformation does. So my transformation t, my rotation transformation, takes a vector xy and sends it to what thing in a linear map? It sends it to x cosine theta minus y sine theta, and it sends it to x sine theta, and then plus y cosine theta. And now, of course, for any of these for any linear transformation, I get a corresponding linear map. And what do? My matrix over here that corresponds to r theta, the matrix m theta for rotation, is going to be r theta at e1 hat, first column, and then the second column is going to be r theta e2 hat. Okay? And so what's our rotation matrix? Our rotation matrix m theta is going to be what? R of E1, I plug in x equals 1, y equals 0, because E1 is what vector? This is the vector x equals 1, y equals 0, and this is the vector x equals 0, y equals 1. And so if I plug in x equals 1, y equals 0, I have a cosine theta, comma sine theta in my first column, cosine theta, sine theta. And then when y is equal to 1 and x equals 0, I have negative sine theta, cosine theta. And this is the mapping, this is the matrix that rotates. So this rotates by theta radians anti-clockwise. Thank you very much.